Hey, this is lab 3, mass of a black hole. In this lab, I was given the position values of a star and was asked to find the forces acting on the star. And I was able to do this, and I will explain this process in this following presentation. So the important equation that we're working with is the gravitational force equation, which is stated right here, where G is a gravitational force constant, M1 and M2 are the masses of the two objects acting on each other, and R is the difference in the position vectors of each. And so, of course, this gravitational force is derived from Newton's second law. And so, one of the more interesting concepts of this lab is that we're going from analyzing motion to knowing the forces of the surroundings on the system, where in previous labs we've used forces to predict motion, but this time we're going the opposite direction, which is more real life and seems more physics-like, experimentationally. And so important concepts to know is that F net equals dp over dt, and that's basically just a Newton's second law rearranged. And F net in this case equals F gravity because we're not considering any other forces, only the force of gravitation, which is acting on the star by the black hole. So here's the VPython code that was used to know the values that were needed to know the mass and the forces acting on the star. On the left-hand side are the givens, such as the star's mass, delta T, and all this is basically just reading the position values of the star. And on the right-hand side, we F net perpendicular, F net parallel, F net were all calculated by taking the position values and from that finding difference in position, and then from that finding difference in velocity and multiplying to find difference in momentum, and then that all comes to give F net, which is F gravitation. So that was a really cool process and was really quickened up by using the coding computer. And here's continued. Basically, the only important thing is that the error scale was changed to 4 times 10 to the negative 16. That's because the forces are so great, so the scale has to be really small to fit it in the page. And here's samples of the motion shown of the star. And here the yellow arrow is the F net, which points directly to the star, since the F net equals F and it points directly to the black hole. And the black arrow is F net parallel, and blue arrow is F net perpendicular. Here's the trajectory a little later in time. It's circled the black hole, and then of course it's slowing down because it's past the black hole and it's still turning towards the kissing circle. Calculation of mass was found by rearranging the gravitational force equation to this right here, and then that was just found using simple algebra, and this is the mass of the black hole that I found. So for the what does it mean question, if F net and F net parallel and perpendicular, those things do not actually exactly equal delta P over delta T. That's because delta P over delta T is simply an approximation by subtracting final momentum and initial momentum over final time minus initial time. And so although it's a really close approximation if you make the intervals close enough, which we did, so they're not exactly equal, but they're close enough for our situation. So for the what if question, if the star that had been observed was moving in the exact same motion, then that means that the new black hole that was in place of the first black hole would have to be identical, because if the second black hole had a different mass than the since the movement of the star is dependent on the mass of the black hole, then it would have different motion if the mass of the black hole is different. So that means that it'd have to have the same mass in this second black hole. In conclusion, observing motion to knowing forces is really useful because you can't actually see forces. So this is a really cool new concept that we'll be using, and fundamental principles can be used to learn many things. Thank you.